to have contact with J. And so one aspect is that contact is random. And then J has to be susceptible. So you can think about immunization changing how fast COVID spreads by changing the percentage of people who are susceptible. So a lot of times in these applications, the focus is on changing. So there are some, of course, there's network structure that will affect how it spreads, but the policy element usually comes from affecting susceptibility. And you can also think about, say, other than COVID, spread of infectious disease, you can think about spread of rumor, spread of an idea, or spread of some product adoption. So now, typically the questions are as follows. Well, the most important question is, well, especially for infectious disease, is will an initial outbreak spread to a significant fraction of the society? So, for example, if you want to implement zero COVID, then what's a threshold? So, once a threshold number of people is infected, then maybe there's no hope. And also, what's a threshold, say, in terms of susceptibility or network structure, like how connected people are, so the contact structure, how does that affect the answer? Like, will it spread to a non-trivial fraction of the society, or will it be contained and eventually die down? Okay, so that's question one. Can you contain it? So will it spread to a significant fraction? Then suppose it will spread to a significant fraction of the society. What's a fraction that will eventually be invented? And yeah, then how does the initial, so these are outcomes, and then we ask about comparative status. How will the initial contact network affect the outcome? And how do potential policies, so here, the intervention here, affect the outcome? So people apply this type of idea to biomarketing. It's like a term, so you try to spread an idea about the existence of a product, like how a virus spreads. So it's spread of product adoption, an idea, a rumor, a faction, etc. So again, it's possible to spread from I to J usually if I has adopted. So I has to be exposed to the idea. And well, if I has been exposed to the idea, when would I be willing to spread it? So here, unlike spread of disease, whether you spread a disease, actually it's not true. I was going to say that a person usually cannot control it, but that is actually not true. You can change how likely you spread the disease by, say, choosing to mask. Okay. So here, once a person learns about a product, when does he want to tell someone else about the product? Well, that may depend on his experience. So then you have to make a call when you model this. So there's and then I has to be friend with J, so I and J have to have contact. So here, sometimes up to now we assume either an exogenously given friendship network structure, social network, or an endogenously chosen network structure. Like individuals can choose whether to create a link at a cost. But here, actually for tractability, and also it's realistic that sometimes whether you meet someone is random. Okay, so we're going to model friendship network as a random graph. So that will be kind of the main technical needs that will be the takeaway from this class. That is the toolkit of using random network. Okay, and then J has to be susceptible. So susceptibility again is affected by marketing strategy. So one, for example, it can be price, and you can also think about these referral benefits. You can pay someone to refer a friend. Okay, so now the questions, similar to the spread of infectious disease, questions are, well, will a tiny fraction of initial seeds spread product adoption idea, fashion to a non-trivial fraction of society? And then the percentage of eventual adoption. And then how would the initial social network structure affect the outcome? And how do potential policies that will be here affecting the susceptibility? You can also think about how the policy could affect, that the policy could also affect whether I would have referred his friend about it. Okay, so this is the application we're going to talk about today. So it's word of mouth communication. It's a paper in 2013 in AER. So they use word of mouth communication. It's the same idea as viral marketing, etc. So the idea is that there are academic papers and consumer survey. I found that many consumers rely on friends' referrals or word of mouth communication to choose to buy some product. And those that engage in word of mouth tend to be those who have adopted. It's kind of so if you say it's hard, you don't see someone who doesn't drive an electric vehicle to advocate an electric vehicle. Usually those who advocate for a product, they're enthusiastic, they really like it, and that's why they tell their friends about it. Actually for quite a long time, so my husband played this game called Witness. I don't know if it's a video game. There are lots of puzzle games inside. The graphics are very, very pretty. And so everyone he meets, he would talk about this game. And so it's, I think how often you would talk about this depends on how enthusiastic you are. But in this paper, they make a 0-1 assumption. You either talk to all your friends about it, or you don't talk to any friends about it. All right. Okay, so the main questions in this paper is that how does the word of mouth mechanism affect monopolists' optimal strategy? So they talk about pricing and advertising, and we're only going to talk about pricing. And how does monopoly strategy, optimal strategy, depend on the network structure? That could be, say, how connected the network is. And you can talk about clustering and the variance of the friendship distributions. Like whether many people have similar number of friends, most people have similar number of friends, or some people have lots of friends, some people have very few friends. So I would say the main point of this, so the application, what I found is that the conclusions they are able to draw aren't that surprising. And they don't hold under all social structures, because you can imagine the network is complicated. So if network structure is different, sometimes you cannot make surprising things can happen. But I think the tool of random network is the most important part of this, of talking but that is a good place to start because it actually has intuitive explanations. But it was I found it more interesting to put it in the backdrop of an application and story. Alright, so here's a model setup of the paper. So a monopolist sells a good to a set of consumers, 1, 2, 3, up to n, at the price P. Consumer I's valuation is theta I, and that is drawn IID from uniform distribution, uniform 0, 1. And the consumer payoff is very simple. She gets her valuation minus the price if she buys it, and she gets 0 if she doesn't. So if she is informed, she will buy the product if and only if her valuation is greater than the price of the good. So it's a very simple demand function. If our consumers are fully informed, the demand function is just 1 minus P. Now the issue is consumers don't know that this product exists. And they rely on word of mouth communication to learn about the existence of this product. So initially, they're all uninformed. And then a tiny fraction, say epsilon, that is very close to 0, become informed about the good. You can think of them as the seeds. Right? So the seeds there, so these are exogenous. So who is informed in this paper is exogenous. And there are papers that talk about strategic choice of these seeds. But here it's just some tiny fraction of the consumers. And the paper is interested in analyzing the distribution, the network, the word of mouth network, in the limit as epsilon goes to 0 and n goes to infinity. So this is what you often do with random network. So when it's finite, it's hard to handle. So what people do is they analyze the distribution of links, the behavior in the limit as the network of size goes to infinity. Okay, so only a fraction epsilon of consumers are initially informed of the good, and then other consumers will become informed only through word of mouth communication. So let's say if I is informed of the product, then with some probability, I will tell all of her friends about the product. Okay, I will inform all of her friends. So it's like you can think of being informed as being infected. So with this probability, I will infect all her friends, and with a complementary probability, I will infect no friends. Okay, and they assume, it's a very simple assumption, if I is informed of a product, she will buy it if her valuation is greater than price. Okay? And they assume that she will inform all her friends if she buys it, okay? If she adopts it. Okay? So if I is informed of the product, I will buy the product and inform all of her friends if her valuation is greater than price. Otherwise, she will not adopt it, and she will not inform any of her friends about it. So you can say that I is susceptible if and only if her valuation is greater than price. Okay? So the monopolist pricing strategy is going to affect the percentage of consumers that are susceptible. And here, whether a consumer is susceptible is independent of the number of friends a consumer has. Okay, so the communication is like this. So let's say here, I is informed, and then if with probability 1 minus P, I will, let's say, beta, I has 3 friends. With probability 1 minus P, I will inform her friends. Okay, J, now J is informed, and then J will, depending on J's valuation, so again with priority 1 minus P, J will inform all her friends. Okay. K has 1 friend, L has 4 friends. So each decide whether they inform more people depends on their valuation. So let's say K will inform her friends, L will not, and J also will, then so K will inform or depending on K, how many friends K has. Okay. So it will spread. And then you look at, we want to know the structure of the word of mouth network at the end. It's like who becomes, so we want to know who becomes informed. Once you know who becomes informed, then you know the percentage of people who buy. Okay. Okay, so one easy way to analyze the word of mouth network is that, well, because we know, given a consumer's valuation, we know if the consumer will inform her friends, will affect her friends if she is informed. So we can look at the susceptible nodes. So what you can do is you can delete the nodes that are not susceptible from the social network. So although this model, so this assumption assumes that, well, whether you inform others, so whether you're susceptible doesn't depend on, so it depends only on your valuation, but not on how many friends you have. But this model allows possible correlation between valuation and number of friends. So it could be that those who so in terms of product adoption, like say fashion, so those who are fashionable might have a lot of friends. So those who have high valuation of certain fashion might have lots of friends. But the results I'm going to talk about assume independence. But just the framework allows correlation. Okay, so each consumer is characterized by her valuation and the number of friends she has. So you can allow correlation. And then from this probability, a randomly selected person has K friends. It's just you're integrating the joint distribution over all possible valuation. And what you get is PK. So in bottom line, you should think of all these distribution to depend on the number of people in the network. So I'm going to write, so PK will be the limit. So you can think of the distribution as the same. The distribution is the same for every n, then the limit distribution will be the same. Okay, so PK is probability a randomly selected person has D friends. I use D because it's links. The number of friends you have is just your link, so your degree. And the probability a person with D friends is susceptible. So previously I say we assume that whether a person is susceptible is independent, depends only on valuation. But if valuation is correlated with number of friends, then whether someone is susceptible will be correlated with the number of friends. So QK, actually, sorry for the inconsistency. For the rest, I use D. The paper uses K, but Jackson uses D. The probability a person with D friends is susceptible is denoted by QD. So it's okay. So from the distribution, the joint distribution of valuation and degree, you can find the conditional distribution. So conditional on the number of friends, the distribution of valuation. And given this conditional distribution, a person is susceptible if her valuation is above P. Okay, then you can find the probability a person with P friend is susceptible. Okay, so if valuation is independent of the number of friends, then QD is just 1 minus P for all number of friends. So now we're going to model social network as a random graph. So the friendship network, so as we said earlier, a network, here we're going to look at undirected network. So we'll say that IJ, the pair IJ is in the network if, undirected just means that if I and J are connected, then J, so I is connected to J, then J is connected to I. And we're going to think of the network structure as drawn from some distribution over all possible undirected network structures with n nodes. And then we're going to consider some specific classes of such distributions. Okay, so in this paper, there are 2 networks. The friendship network, that is drawn randomly from some distribution. And then there's a word-of-mouth network that arises from the friendship network, the realized friendship network, and the monopolist pricing strategy. So given the friendship network, you keep only those that are susceptible, those whose valuations are above the price, then you drop the other nodes, the other nodes that are not susceptible. Okay, and those susceptible nodes, they will engage they will spread the information if they're informed. Okay. So now the question is, we want to know, so let's say here is realized network. And so suppose I learned is informed, then, so say this is a social network, and then what you do is you delete those that are not susceptible. Let's say K is not susceptible, so you delete this one. But if you delete that, then these 2 are not linked. So you start, and then you can do the same for this part. And so now if I is the only one that is informed, then since the people who are left are susceptible. So if their friends are informed, then they will be informed and they will spread it. So if I is informed, I will tell J will tell her friends. I will also tell L will tell her friends. And this one is not susceptible, so we're going to delete it. Okay, so this guy was K's friend, but K is not susceptible, so K is deleted. So there's now no path from I to this guy. Okay. So suppose I is the only one who is the seed initially informed, then this guy will not learn about it. so for this purpose, we need to understand the behavior of sets of nodes that are connected. Okay, so let's see. So that's called components. Okay, so in this picture, there are three components. This is one component. Okay, so and this is another component, and this is another component. A component is a subset of consumers such that for like any two consumers in the component are connected. So for any two consumers in the same component, you can find a path from one consumer to another. But for any consumer, if you take one consumer in a component and another consumer outside of a component, there's no path from one to the other. So a path is just a sequence of nodes such that for every two consecutive nodes, they're linked. Okay. Questions? Okay, so now here's a relation between whether an idea will diffuse to a significant fraction of the society or not, and component size. So, yeah, so I already said the first part, that if I is seeded, and if I is susceptible, then everyone in the component of the word of mouth network I belong to will eventually become informed. Okay. So now if the component size is bounded, so uniformly bounded even when n goes to infinity. So if the component size is below some finite number n for all n, then the fraction of those who eventually become informed will be smaller. So let's see. So there are n people, and epsilon n of them will be seeded, will be the seed. Okay. So now sorry, there should be just this one. So there are n. So epsilon fraction of the whole society is seeded. Now m over n is a fraction. So what we want to know is, well, how many people in this component? So, or what's the probability at least one person in the component will be seeded? Okay. So let's see. They say this component size, let's call this as is smaller than n. Okay. So as the number of consumers grow, of course the component size is going to change. So let's say the component, if this component it remains below n for all n, then we want to know what's the probability that someone in this component is seeded. Okay, so we know epsilon is a fraction that is seeded. So if there's one person, then with probability epsilon, that person will be seeded. And epsilon is, it's epsilon of the fraction. It's epsilon n, and they're interested in epsilon going to 0. Okay. All right. Okay. So there are some. For every, so if there's one person, then on average epsilon of this person will be seeded. There are n people. So there are n people in this component with the epsilon, each individual is seeded, so the expected number of seeds in this component is epsilon times n. So that's the average number of seeds. And as epsilon goes to 0, this will go to 0. So the average number of seeds in the finite component goes to 0 as the fraction epsilon goes to 0. So what we need is that it's just binomial distribution. You can see that the probability that one person is seeded in a finite component is going to go to 0 as epsilon goes to 0. Okay. So if a component is bounded, then in the limit as epsilon goes to 0, the number of seeds goes to 0, the fraction of seeds goes to 0, this component, the probability this component will be informed will go to 0. Okay? So the point is, if anyone that belongs to a finite component in the limit will not be informed. So in the limit, as epsilon goes to 0 and n goes to infinity, who will be informed? Only those who belong to components whose size grow at least linearly with n. So these components are not bounded. So their size grows at a rate at least some number r greater than 0 with the size of the social network. Okay, so what we're interested is to know the fraction of people. So these the components that grow at least linearly with the size of the network, and it's called a giant component. So a giant component may not exist. So to know whether the idea will diffuse to some non-zero fraction of the society as n goes to infinity, we need to know if a giant component exists. And then to know, well, what's a fraction of the society that will eventually become informed, we want to know the fraction of people in a giant component. Okay, so most of the efforts are spent on analyzing the behavior. Well, you're counting. We want to count the number of people in the giant components. But those who are in giant components are not in. So a bounded component is called a small component. That's next slide. So let me just finish talking about this slide. So S upper bar is the size of the largest component of the word-of-mouth network. So yeah, so this is what. So if S upper bar grows at least linearly with n, so this actually is greater than or equal to r. So if the ratio, the fraction of people in the largest component well, it has to be at least, it cannot be bigger than 1. So in the limit, if it converges, it will converge. So but if it doesn't have to converge. If it remains above some number r, for some positive number r, then by law of large number, eventually at least one consumer in the largest component of the word-of-mouth network will be a seed. But then everyone in this component will then become informed, because there is a path from the seed to everyone in this component. Okay, so then we know there's the fraction of at least r will eventually become informed. giant component exists in the random graph with a degree distribution, pk, if the fraction of nodes inside the largest component remains bounded away from 0s and goes to infinity. So what we're going to do is to count. We want to know, okay, if we can calculate the fraction, well, because the giant component, the number of people in the giant component, if it exists, grows without bound, and that is hard to handle. So what we do is we count the number of people in small components, and then once we can count the number of people in small components, we can calculate the fraction of people in small components. Then those who are not in small components are then in the giant component. So if we can calculate the fraction of people in small components in the limits, then we know the fraction of people in, well, we know whether a giant component exists. Or if a fraction is 0, then it doesn't exist. And if a fraction, if a giant component exists, then we can calculate the fraction of people in the giant component. Okay, so we're going to spend some time on theory of random graphs. So what we'll do is we'll talk about theory of random graphs, and then we'll go back to this model to talk about monopoly pricing. Yes.
I confirm, like, why do we care about smaller components? Like,
so because if so a component is either small or giant. So what we want to know is the fraction of people in giant component. But because it's easier to handle small components, you'll see in a bit why it's easier. So what we do is we calculate the number of people in small components, and then we know the fraction. Then those who are not in small components, the fraction 1 minus the fraction of small components will be the fraction of giant component.
so this giant component is not restricted to one giant component. It can be multiple.
No, there can be multiple, but there really will only be one. But this, so for our purpose right now, it doesn't really matter how many giant components there are, because if a component is a giant component, then the number of people in this component grows at least linearly with n. Okay. So if a fraction, probability any individual is seeded as epsilon, then so for fixed epsilon that is positive, in the limit as n goes to infinity, then at least one person, even if there are two giant components, in each giant component, at least one person is seeded. But since we're talking about giant component of the word of mouth network, we delete nodes that are not susceptible. So if there's one person in this component that is seeded, everyone in the component will be informed.
Somehow
So it's not saying we're all in the component.
Yeah.
So that means for any two people, there's a path. Say there's a path between me and you. It could be that we go through everyone here. But since we're all susceptible, that means if any of us, once becoming informed, we will tell all our friends. Okay. So let's say I'm the first one informed, then I will tell I'll tell Joyong, and then Joyong will tell Red, and Red he will tell Shuhan, and Shuhan will tell you.
So we probably want.
Yes, we'll probably one. So it's for take any component, as long as one person is informed, So that's why we need to know the distribution of component sizes in the word of mouth network. So we delete those who are not susceptible because they won't spread the news. So it's as if there's no link. Okay. Yes, but questions are very good. Is it good? Yeah? Okay. So here I think we can do this because it's a 0-1. Whether you tell your friends or not, it's a 0-1 question. So then we just delete those who will not spread. Then anyone who remain, if there's a path between them, then information will spread from one to the other. So we just, as long as one person in the component is infected, everyone will be infected. And so we want to know the size. So if the component size grows at least linearly with n, then in the limit, probability that one person is infected is 1. So then the probability that this whole component is infected is 1. It's infected eventually.
So the goal of this paper is just to characterize network for any graph theory, not about some design problem.
They want to know about the design problem. So the paper actually didn't spend a lot of time on the graph theory. So what they want to do is they want to look at monopolist strategy, taking into account the fact that their strategy is going to affect the word of mouth network. Because here, whether a person is susceptible depends on price. So, of course, if I lower price, a person is more likely to buy. But if I lower price, there's another effect. A person is more likely to be susceptible. So if a person, so that means the word of mouth network will be bigger, you have more nodes. So if it has more nodes, then the structure, the network structure is going to be affected. But then how does changing P or through affecting susceptibility affect the network structure depends on how the number of friends interact with theta. Because you're susceptible if you have high valuation.
So in terms of economic context, it's more like if I'm willing to buy it, I'm willing to share it.
This is what they assume.
Okay.
Yeah, so this is their assumption. If I'm willing to buy it, I'm willing to share if and only if I'm willing to buy it. So you can change. So in terms of economic content, some of the results are not that surprising that they can find. But I think the tool, because there are a lot of things you can play with, and depending on the application. So susceptibility, and how would the policy affect susceptibility? So talking about, say, fake news. Okay. So the people have been throwing around the idea that they call it immunization. So instead of doing fact checking, like you're running after fake news production, another strategy is you can think of it as changing the probability a person is susceptible to fake news. Is more likely to spread the fake news. So then you can think of like telling them, informing them, and that will change the condition that they will share. You can also think about changing the structure of how fast or how wide or the spread of the news, and that will be affecting the network structure. So depending on the application, there are quite a lot of moving parts you can change.
I missed the third point, the third possible. I only focused on the probability DI.
Yeah, so here they make a very simple assumption about this function. So yeah, whether you tell your friends about, whether you share this existence of the product depends on your valuation, like something interesting to you and some policy the monopolist chooses. They can talk about advertising, and here they make a very simple assumption, but you can imagine some other function. But of course, tractability is an issue.
So when one of the agents within the large network are informed, then everyone within that network will have the same valuation.
No. So valuation, everyone's valuation is independent. But if you are susceptible, then you have your valuation are all higher than P. So if you're two people who are susceptible, their valuation will be correlated because they're both higher than P. But they don't have the same valuation. They just have valuations higher than P.
So what do we do with the information? Like we have so our valuation is not just dependent on information, or is it?
The valuation does not. No. So it's not like the learning where you learn something about the product. No, your valuation is different. It's just private valuation. It's a question of whether you know the existence of the product. So so learning games are usually about like learning something about the fundamental that is important to your decision making. And this diffusion games, usually it's you don't know something exists, and then you become aware that something exists. So or it's opportunity to make a decision. So it's the information is useful because if you don't have the information, you cannot act. Yes. So it's really like spreading a disease. So yeah, I think the model of spreading disease comes first. And this paper, the paper that it mentioned is actually a physics. It's in physics journal. So yeah, I think they call this percolation theory that is supposedly in physics. So it's whether the probability that something will travel from one side of the object with holes to the other side. And holes make